Hello and welcome back to our video lecture series on in Chemistry 1331 Spring Semester 2020 during the COVID-19 stay-at-home shutdown. I hope everything is going well for you. If you're paying attention and keeping up with the class, I'm sure everything is very difficult right now. We're all doing our best to try to get the university going again and come back to some degree of normalcy. So thank you for joining. I hope these video lectures are useful to you. Again, as a incentive to pay attention to and watch the videos, if you subscribe to the video lecture series, I will record this, and as I mentioned this earlier in the lectures, I have the option of giving out a number of extra credit points, a few, not many, here and there, and I will give you one if you subscribe. And this is not only a great way to boost your grade a little bit, but also keep up with the class and do everything else to keep up and move ahead. I'm not going to talk about the Dalton's law of partial pressures. It is something you'll need to know. It's actually quite simple to just go through the lecture notes that I've uploaded in the PowerPoint slides under this zoomed all PowerPoint Chapter 8 edited PPTX that I have, and just work through the problems. It's really not that hard. It's simply an application of the ideal gas law, and in a nutshell, a partial pressure is simply the statement that the total pressure of a system is the sum of all the partial pressures, and the partial pressure is simply related to the number of atoms, or what's called the mole fraction. What fraction of the total number of moles in a gas sample correspond to that particular molecule or that particular atom, and the sum of all of those is the total pressure. So just simply work through those. It's very simple to go through that, and I can make a separate lecture if we need to. I apologize if there's any background noise. There's some mowing going on outside my house, and that's just the way it goes. Okay, so today we're going to talk about the kinetic molecular theory of gases, and this is the basic connection between what we were talking about earlier in the class with the atomic theory and all that, with thermodynamics and what is ultimately called statistical mechanics. So I'll mention a few of these concepts throughout, but this is really a core foundation of how we think about the molecular theory of gases. The basic kinetic theory, and I think I've stated this before in a number of times throughout the class, is that the basic postulate of modern chemistry, or really physical chemistry, is that all matter is composed of atoms, which are indivisible particles. Under normal chemical transformations, they're indivisible particles. These atoms are in constant motion, even at 0 degrees Kelvin, which is due to quantum mechanics, and they collide with each other, they occupy volume, they repel each other at short distance and attract each other at long distance. And we're going to use that to establish what's called the kinetic molecular theory. And in order to make headway within this, we need to abandon a few of the statements that I mentioned earlier in this. Now, first of all, we're going to assume is that the size of a molecule or size of an atom is really, really small compared to the volume that it occupies in for a gas molecule. We can calculate, if we want, the average space and the average distance between atoms in a gas, and it's rather straightforward to do that. In a liquid, that's not the case. In a solid, that is not the case. The spacing between atoms in solids and liquids is on the order of about a chemical bond length, 1 or 2 angstroms away from each other. In a gas, that is not the case. They're more like 10 to 20 to 30 or 40 angstroms away from each other in a typical gas. In fact, we can calculate what that happens to be pretty easily. The molar volume of one, or the volume of 1 mole of an ideal gas is 22.4 liters. Remember, a gas is 10 to 1 mole is 10 to the 26 times 10 to the 23rd atoms. in that gas, or particles in that gas, and so you can divide up 22.4 liters into 6.02 times 10 to the 23rd individual volume elements and calculate the average volume element occupied by an individual gas atom. And it's pretty small. I mean, it's actually, it seems like it's small, but it's actually a lot of space compared to the size of an atom. Okay, so this number 22.4 liters is a number that is important, and it's also important to understand that is at the standard temperature and pressure condition. Remember, standard temperature pressure, STP. Standard temperature and pressure is 300 degrees Kelvin equals the standard temperature, and 1 atmosphere is the pressure. These are the standard temperature and pressure conditions. And 1 mole of an ideal gas has a volume, a molar volume, if you want, of an ideal gas is 22.4 liters. Now we could figure out exactly how much volume an individual atom occupies. Let's just do that really quick. So 22.4 liters is so 22.4 liters is equal to 22.4 times liter is 100 by 100 by 100 is 1,000 cubic centimeters. Okay, that's 1 liter. So this is going to be useful because we're going to allow us to get this into units of that we want. Another thing which I should point out, I fixed the problem with my webcam. I hope I adjusted the lens focus on this. So remember, so 1 mole. So the density of an ideal gas, rho, is the number of atoms divided by the volume, and that is going to be 6.02 times 10 to the 23 atoms. That should be a capital N, divided by 22.4 liters. That's atoms per liter, numbers per liter is the density. So now I can do this very easily, 6.02. Let's just use Mathematica to do this rather than pull it out on a calculator. 6.02 10 to the 23 divided by 22.4 liters, and that gives me that the density is this is now the number of it's the number density of atoms per in number of atoms per liter. Okay, so 2.6875 times 10 to the 22 atoms per liter. So this is the density. This is density equals 2.68 times 10. This is put 3 significant digits. So it's 2.69, 10 to the 22 atoms per liter, right? So what does that mean in terms of a space? Well, I can start dividing this down. So this is going to be 2.69 times 10 to the 19 atoms per cubic centimeter. Okay, so one centimeter is equal to 10 to the 10, 10 to the minus 8, 10 to the 8th angstroms. Okay, so now a cubic centimeter, 1 cm cubed, is 10 to the 24 angstroms cubed. Okay, so now I can convert this into the densities per cubic angstrom. Rho is equal to 2.69 times 10 to the 19 atoms per cubic centimeter And then 1 cubic centimeter is equal to 10 to the 24 angstroms cubed. So I can put this, 10 to the 24, 10 to the minus 24 centimeters cubed per angstrom cubed. And now I can easily multiply this. 2.69 times 10 to the minus 5, right? Atoms per cubic angstrom. Okay, so there's not that many angstroms. So again, if I look at this on the average spacing between atoms, so in other words, if this is the typical a small atomic volume or bond length, there's not that many atoms around you in a gas. It's very, very low density compared to the typical bond length of a molecule, which is about an angstrom. Okay, so I can then maybe I can take the cube root of this, which would be something like about 1 per 10 angstroms, basically. So it's about an average distance between each one, about roughly 10 to 20 angstroms between atoms on average in a gas. So we can easily figure out about the number, how far apart atoms are on average in a gas. So very, very far away from each other in a gas. Okay, so which makes sense. Now, so if you put this into the perspective of our approximation, this would be like saying if the students on the University of Houston campus were spaced accordingly to that of an ideal gas, we would have roughly 1 student on maybe 10 or 15 students on campus at any given time. That would be about the density of an ideal gas in terms of your volume versus the area, or roughly volume, if you would, of the University of Houston. So not a lot of collision. So this is a pretty good approximation. So we can really think this is a comfortable approximation. The second thing is that atoms are in constant motion. Pressure occurs in the following way. So usually we think of pressure as being something, well, we're pushing the atoms out of the way, or the atoms are bumping into each other, and that is giving rise to the pressure, like my glass here, right? So I've got this glass, your masters of malt glass, and I put pressure on it by squeezing it. It's I'm the atoms and molecules in my finger are squeezing actually on the electron density of the glass, and it's trying to push it out of the way. That's not the case in a volume of gas. I really have atoms that are moving and atoms that are colliding with the wall. Here's a wall, and maybe I can think about this as like a piston. Here's a container. Okay, here's a piston, and I have a force, an external pressure pushing on that piston, and I've got gas molecules inside of this bouncing off the walls of that piston, causing it to move forward a little bit, move backwards a little bit. And it's the fact that I'm constantly trading momentum between the motion of the gas, and this is of course in some sort of rigid wall type system like that, and it's pushing outward, and then I have an internal external pressure, and eventually this internal pressure, P internal, equals P external, and this piston stops moving. Okay, this is how a piston works. Okay, and the next thing that we're going to assume is, because the gas atoms are so far away from each other that they exert no interaction with each other. So insofar as the ideal gas law is concerned and the molecular kinetic theory goes, gas molecules do not interact with each other. There's the long-range part of the potential is effectively zero, and the short-range part of the interaction is taken to be negligible. Okay, so that's the next thing. And then the third postulate is that the average kinetic energy. Okay, so what is the average kinetic energy And this I'll talk about in a moment. The average kinetic energy, which I'll write as KE, with little brackets around it like this, so you know it's the average, is, well, it's going to be 1/2 times the mass times the average velocity squared. Okay, and this is going to, we're going to show that this is going to be proportional to, in fact, it's going to be equal to 3/2 times a constant called the Boltzmann constant times the temperature. KB, called the Boltzmann constant, and the Boltzmann constant is a number we need to look up. And the Boltzmann constant is this number here, which I'll give it to you here. The KB is equal to 1.38 times 10 to the minus 23 joules per Kelvin. And it turns out that the gas constant, ideal gas constant, is equal to the Avogadro number times KB. Okay, this is the ideal gas constant. This is 8.02 or 0.26, excuse me, whatever the number is, 0.082 liter atmospheres mole Kelvin type constant, liter atmospheres mole Kelvin constant we talked about before, right? So just simply multiply these numbers and you will get the gas constant. It's the ideal gas constant. The Boltzmann constant is a per atom type quantity, and it's simply a conversion between Kelvin and joules. And so the average kinetic energy is proportional to the temperature of the system. So in other words, it's the hotter I get, the faster the molecules or atoms are moving around. So as a quick little concept, we can imagine over here we have two balloons, one with helium and one with hydrogen, each holding the same volume. Okay. And we want to ask ourselves a couple of questions. So each has the same volume, and roughly let's think about it. The mass of helium is roughly twice that the mass of, well, the mass of one helium atom is roughly 4 proton masses. So it's roughly twice as heavy as hydrogen. And so a couple things. We'll assume that the balloons are the same. So the pressure inside of the gases, inside the balloons, must be the same because they have the same number of moles, same moles of atoms, so same moles of particles. You know, 1 mole of helium, 1 mole of hydrogen. The temperatures will assume to be the same. The numbers of moles are going to be the same. However, the densities are going to be different. The mass density. Okay, so the mass density in terms of grams per liter will be different because helium is heavier than hydrogen. Okay, it's twice as heavy as hydrogen. So in principle, the mass density of the particle will be different. So actually, so maybe the better way to however, on the other hand, the number density, the number of atoms per volume, will be the same. The helium one will weigh more than the hydrogen, and so consequently, actually, hydrogen is a great gas for example, making dirigibles and making helium or making balloons, because it's more buoyant than helium. However, it has a small problem of being very flammable, so it's not necessarily a great thing to have as a way of lifting a balloon. Okay, so we can go through Boyle's law, and again, Boyle's law is simply more just a restatement of the ideal gas law. PV equals nRT. If there's one equation you need to know for this particular section, PV equals nRT. Just remember this. Okay, as the volume decreases, the pressure increases. That's the Boyle's law. And so, according to the molecular theory, if I squeeze on this piston here, and it's now a smaller volume inside of here, okay, make that a smaller volume, I have to put pressure on this whole thing, but I have a smaller volume. So I increase the pressure, I push in on the piston, the volume decreases. Again, these are very simple concepts, and if you're confused by this, just draw yourself out a piston, or better yet, make one for yourself and demonstrate this for yourself. This makes sense, okay? And likewise, pressure is proportional to the temperature. So as I increase the temperature of the molecules or gas atoms inside of this little volume, I get an increased pressure. It's going to push this out. This is how your car works. I combust a gas inside of a piston, increases the pressure inside the piston, pushes out, and it is then transferred into mechanical energy that's used to propel your car or other sort of motors. As the temperature increases, the speed of the particle is increased. You hit the wall with greater force, and the result is increased in pressure. An easy way to demonstrate this is to have everybody in the classroom put on blindfolds and start running around randomly, and run around slowly, and then run around very fast, and look at the number of times you hit the wall. The more often you hit the wall, the higher the pressure, and the harder you hit the wall, the higher the pressure. Again, makes perfect sense if you simply think about this in a maybe a less abstract and less mathematical sense, but just in terms of the physics of what's going on in this system. And lastly, Charles' law. Charles' law is related to the ideal gas law. V is proportional to temperature, with nR over P being a constant. Again, all of this is simply the ideal gas law. PV equals nRT. Look at what's being held constant and rearrange as you need. And lastly, this is the Avogadro law. Again, PV equals nRT, simply rearranged a little bit, gives you the law. So all of this is completely consistent with the ideal gas law, and Boyle's, Charles, and Avogadro laws as well. So, again, this here's our picture of our piston. As I put gas molecules into the piston, in other words, like if I blow the tires up on my bicycle, I put more air into my bike, I get a higher pressure, it pushes out on the walls of the tire, and I inflate the balloon, and I inflate my tire. Now, Dalton's law says that the total pressure exerted by the mixture of gas is equal to the sum of the individual pressures the sum of pressures of the individual gases. And so maybe it was worthwhile to talk about a little bit in terms of Dalton's law. Dalton's law is again very, very straightforward. Dalton's law is that the total pressure is the sum of the individual pressures, P1 plus P2 plus P3. So one of my little strange idiosyncrasies that I have is that my uppercase P's look like this, and my lowercase P's have these little tails on top. I don't know where I picked that up. I've just been doing it for the last 40 years, I guess. So anyway, that's what this means. The individual partial pressure. So the reason this works out from the theory of the kinetic theory is that gas molecule of species 1 really doesn't know anything about the other gas molecules that are in the system. It's moving around as if it sees a full volume and exerts a pressure. Gas atom number 2 or species number 2 doesn't know about 1 or 3 or whatever else that happens to be in the system, and it's moving around blithely, not knowing that there's other things in the system, and likewise. And it doesn't matter. The individual volumes are not important. It's just that, and so it's the sum of the total partial pressures of the individual of the thing. So you can understand this in a very simple way. If you could say that the pressure times volume, say this is the partial pressure of species I, this is the total volume of the system, is equal to the number of moles of species I times RT. Okay, and the total number of moles is N1 plus N2 plus how many different moles that I have. So I can then say that I have each one of these in the pressure total times volume is equal to N total times RT. That doesn't change. And so consequently, I can easily write this out as P1 plus P2 plus P3, all these other guys, times the total volume is equal to N1 plus N2 plus N3 times RT. And that's all that it is. And I can define a mole fraction is simply chi, is our general, the mole fraction of species I is the number of moles of species I divided by N tot. So it's a dimensionless number. And so the partial pressure is simply the mole fraction times the total pressure. Okay, that's all. That's Dalton's law, and the assumption of that is that each one of these partial pressures, each one of these gas species, are independent of each other. They have an individual pressure associated with each one, have an individual number of moles of each one. Temperature is the same, volume is the same. They're all moving in the same volume V and at some constant temperature. And that's the only thing that matters insofar as this is concerned. Now, we can use the gas law in the following way. So this is sort of a backwards way of deriving this, I think, but we can do this in let me walk through this, because I don't like the way this is defined in some ways. So let's first of all start off by understanding what is meant by a distribution. So gas molecules have a distribution. So we have a distribution of velocities. Okay, just like since we're we're looking at the we've seen graphs of the infection rates and the numbers of this and numbers of this for COVID and all this. We're getting the idea. I think pretty much everybody at this point or another has seen a bell curve or a curve that might look like this. So this is the velocity, okay, and this is maybe the probability of that velocity. I get a curve that looks something like this. Okay, and and so the probability of moving at velocity here is equal to that number. And I'm going to write this as in the following way, so that the probability of moving in the velocity in the x direction is going to be proportional to e to the minus the kinetic energy divided by the Boltzmann constant times t. Okay, and there's a proportionality constant that's necessary so that the area underneath all of this is equal to 1. And so I'm going to write this out in the following way. It's proportional to e, the exponential e, minus mass times the velocity in x squared divided by 2 kbt. Okay? Now, atoms can move in x, y, and z. And so the total kinetic energy, the total velocity, so v squared is vx squared plus vy squared plus vz squared. Okay, and I'm going to, I need to integrate over all possible x, y, and z velocities. So I'm going to do a little trick. So I'm going to write that the probability of moving at velocity v, I have to be careful the way I do this, is equal to is equal to the following. So I can move in x, y, and z, but I'm going to transform this into a polar coordinates in the following way. So it's I need to do this. So I'm going to write out write this out in the following way. I'm going to write this as a e to the minus velocity squared over 2 kBt times velocity squared, and I need a dv here, dv, and I need to multiply this by 4 pi. And the reason for that is as I'm going to go from moving in x, y, and z, so that I'm moving in only positive velocity. So this is like the speed, if you want. So v is the speed. There's a velocity. So I can then say that and this is still a proportionality constant. Okay, this is a little alpha proportionality. Let me write this one more cleanly. P v dv is proportional to 4 pi velocity squared e to the minus velocity squared over 2 kBt. Okay, dv times the dv. And this proportionality is important because I'm going to require that the integration over all speeds, pv dv, is equal to 1, so that the probability of observing any molecule moving at any speed is 1. I have to observe something. Now, this is a probability distribution. If I make a plot of what this probability distribution happens to be, I get a plot that looks like this. And I'll do this right now. So here I have plotted out the probability as a function of the speed of an atom. In this case, it's a carbon-12 atom. Oh wait, I'm sorry, I need a mass up here. There's also a mass. There's a mass. Okay, there's a mass. I forgot that mass. Okay, of a carbon-12 atom at 500 degrees Kelvin, 300 degrees Kelvin, and 100 degrees Kelvin. 500, 300, excuse me, 500, 300, and 100 degrees Kelvin. The average speed. So let me point out a couple things about this distribution. First of all, this is a speed, so I don't have negative speeds. I can only have positive speeds. As I increase the temperature, the most likely speed. So let me draw out this curve like this. Okay, just to give an idea. If this is the speed, and this is the probability of the speed, I get something that goes up like this and comes down like that. The most likely, the most probable speed. This is the most probable speed. Okay, it increases as I increase the temperature. Okay, it's the peak of that distribution. The average speed. Okay, to calculate the average of something, if I have a probability distribution, if you do this in the way we would do this in statistics, we would write this as v minus 0 to infinity. The v squared is already in there, so p v dv, and I can do that interval quite easily. And if I do this, I'll just cut to the chase a little bit and do this by Mathematica, because this isn't a calculus class. We can do this by hand. What we get is that it is equal to, I'll write this out like this. This is equal to the square root of 8 over pi kT over the mass. Okay, so increasing the temperature increases the average speed, and as goes as the square root of the temperature. So if I want the average speed is now proportional to, let's write this as a constant of proportionality, the square root of the temperature. It's also, the average speed is proportional to, let's write it like this, temperature divided by the mass. Okay, that makes sense, because if I have a heavy atom, it's moving slower. If I have a hotter atom, it's moving faster. And the velocities that I have in this plot down here are all in meters per second. Now, to put that into perspective, 500 meters per second, what does that mean? Well, 40 meters per second is 100 miles per hour. Okay, 20 meters per second is 50 miles per hour. And that is someplace down in here. Okay, so if you were a car, your mass of your car is pretty heavy, and it's not moving at kT. It is not moving as an ideal gas. It's moving way, way down here. So a typical gas atom is moving 10 times, 100 times faster than your car, on average. On average. It's important to point that out. On average. Now, the kinetic energy, the average kinetic energy, so average KE is equal to 1/2 mass times the average speed squared. And now this average speed squared term, we have to be careful when we do that calculation. It is equal to v squared p minus infinity to 0 to infinity. And that we will get very easily. Again, I can do this by Mathematica. I could do this by hand if I wanted to, but again, I don't need to demonstrate my ability to do calculus to you guys. When Mathematica is nicely available, the average v squared is 3 over m kBT. So so what that means, so this is actually a measure of this width. This is related to s squared. Okay, that's related to how broad that distribution is. So as I decrease the temperature, this distribution narrows, and you can see that in my plot over here. As I decrease the temperature, the distribution of speeds decreases. And therefore the average kinetic energy for an ideal gas is 3/2 kB times T. And you notice that is independent of the mass. Mass cancels out in all of this. This is independent of the mass. This is the average kinetic energy. So when you measure the temperature of a gas, you're actually measuring the average kinetic energy of that gas. Okay? And that's what we have back here. So now pressure we can write out in the following way. And I'm not going to go through how we arrive at where the 2/3 part comes about, but we can get it in the following way. It's like the following. So if I look at this expression, pressure, let's pull this apart. Pressure is equal to 2/3 times NNA over the volume times the average kinetic energy, right? This is that's the average kinetic energy. Okay, so what do we have here? So this is equal to N times NA divided by volume. This is the number density. Okay. So we can understand this in a very easy way. So this is the number density. So the higher the number density, the more collisions per second against the wall. Okay, pressure must increase. The 2/3 part actually has to come about due to, first of all, dimensionality and the fact that only atoms moving in that direction, if colliding with the wall, contribute. So an atom moving in that direction doesn't collide with the wall. It might collide with the wall over here, but it doesn't collide with this wall. It doesn't provide that direction of the this is actually where the 2 part comes in. So you're taking 1/2, and then 3 comes about because of dimensionality. Okay, so this is just the number density. This is the dimensionality, really, a prefactor, and the number density times this. So increasing the number density, more collisions per second. Increasing the temperature, faster collisions. That is the origin of the pressure. So PV divided by the number of moles in the system is equal to 2/3 times the average kinetic energy. Okay, so I like to use this little bracket notation for instead of writing KE average. It's just simply a more standard nomenclature, and it also connects to how we would do this in quantum mechanics. So KE average is equal to average KE in these little corner brackets that look like that. So this is simply whatever I have in this is my average. Okay, that just simply means I've taken an average, and consequently, it again in the notation that they have here, U squared with an overline in my notation would be U squared like this, and that is the average velocity. Okay, squared. Now, and it's also important to note that, well, let's write this. Let's say U quantity squared is not equal to U squared averaged. Those are not equal to each other. Okay, if you've had a course in statistics, maybe you might recognize this as the mean, and this is like the variance. This is the variance about the mean. And you can also have the standard deviation. Standard deviation which is going to be the variance minus the mean squared. That's a standard deviation. So again, like when you take an exam, you get an average, the mean, and people always, oh, what's the standard deviation? What's the standard deviation? What's the standard deviation? It's the variation about the mean, and you can also have the RMS deviation by taking the square root of this number that then puts it into the units. So if I have an average with plus or minus 5, that plus or minus 5 is related to the standard deviation. That's the variance, the RMS deviation about the mean. So there's a lot of concepts in terms of statistics that have to be thought about when you're dealing with these kinetic models. Okay, so anyway, so what we get out of all of this is finally we have PV divided by N is equal to 2/3 of the average kinetic energy. Can't draw today. PV over N is equal to 2/3 the average kinetic energy, which is equal to 2/3 times 3/2 kBT, right? And so therefore I get an agreement between the gas law, and this is again, this should be an N, so PV equals N, number of moles, Na times kBT, and this is just the gas constant, R. Okay, that's a simple derivation of the ideal gas law from basic kinetic theory. We can also derive it from quantum mechanics and all other kind of ways as well, but this is the classical way of deriving this. It also gives you a meaning of what temperature is. Temperature is specifically the temperature of a gas, T, is now proportional to the average kinetic energy. right? Because the average kinetic energy is equal to 3/2 RT for 1 mole. This is per mole. Okay, this is a molar kinetic energy, so the average kinetic energy per mole instead of per molecule is that. So a mole of it. So if I know the if I know I have 1 mole of gas and I know its temperature, I can calculate directly its average kinetic energy. Okay, again, this is looking at this as the root mean squared velocity, the RMS velocity. So his notation, u squared, which I was writing as velocity squared, okay, is the average of the squares of the particles. Okay, so and this number, the square root of v squared is the r root mean squared velocity. And so I can obtain that very easily. I know that that the kinetic energy, the average kinetic energy, is equal to 3/2 RT, and that's equal to 1/2 mass times velocity squared. Again, this is going to be in a molar quantity in terms of per mole. If I wanted to put this in a per atom, I would need to do this KE is equal to 3/2 KT, K Boltzmann, times T, and that's now equal to 1/2 mass times the velocity squared, average velocity of an atom. Actually, I prefer doing this on a per atom basis rather than dealing with it per the molar quantity. This is always going to have to be joules per mole or something like this. This will be a much smaller number because this number is 10 to the minus, or on order of 10 to the minus 23. This you'll get in quantities of joules per mole, and a little more palatable number if you want. But this is on a per average kinetic energy per atom is given like this. So now I can say that the velocity squared is simply equal to, well, the 2/2 cancel out, kBT divided by mass times 3. And then simply take the square root of that to get the RMS value of this. That gives you the RMS. So the RMS velocity is simply the square root of this thing. Right, 3/2. And again, I can put this into a molar quantity, or I can put this into individual atom quantity. We'll do it 3. This right equals square root of 3 kBT to 3 divided by mass. That's the VRMS, which is what similar to what we derived before. Okay, so this is the RMS velocity. It's related to the width of this distribution. So this is the root mean squared velocity is related to the width of this distribution. As I increase the temperature, the RMS velocity increases as well. So I get a higher RMS velocity. Again, I can calculate these easily if I wish. Like I said, I prefer doing things in terms of an atom basis. If I were to do this in the way that it's given over here in the PowerPoint, this is the atomic mass. If I did this in terms of the molar mass, the RMS, 3R T over the molar mass. This is now the mass in kilograms. Okay, the molar mass in kilograms, mass of 1 mole in kilograms. And again, the only thing that I've done is I've multiplied the top and bottom by Avogadro's number, right? So the only difference between any of this is that 3 kBt divided by mass, the atomic mass is equal to 3 Avogadro's number kBt. Avogadro's number times atomic mass is now equal to 3 RT divided by the molar mass, the mass of 1 mole in kilograms. That's the only difference between the two. So it's so however you wish to do this calculation. This is probably a little easier to type into your calculator, but in principle you'll get the same number at the end of the day. So we can do this as a simple example. Always do the temperatures in Kelvin. The gas constant, we wrote it out earlier, and one set of units, the gas constant in energy units is equal to 8.33145 joules per K mole. Okay, and that's simply just multiplying the Boltzmann constant by Avogadro's number. That's the gas constant in joules per Kelvin mole. And so then it's simply a matter of plugging things into your calculator at this point. So if I have RMS velocity of a gas of helium at 25 degrees Celsius, I convert it to 298 Kelvin. Convert the mass into kilograms. This is the number of kilograms per mole, and now I'm off to the races. It's simply a matter of plugging things in, keeping track of all of the numbers that you plug into your calculator correctly, and taking a square root properly. And again, this is 1,000 meters per second, which is pretty fast. 1,000 meters per second is roughly multiple thousands of miles per hour. So gas molecules are moving pretty fast. So one of the things that you could do, to get a good concept of this, is to, like I did here in Mathematica, Mathematica is free to download for you. You can go to accessuh.edu and get it, or get this in other plotting routines that you would. But simply make a plot of these quantities and look at how this is now the probability distribution changes with temperature. We can look at this in other sorts of ways as well. But simply make a plot of pressure versus volume, and all of just simply make plots. If you need to understand a concept, make a plot. Okay. We have a sample of gas, and again, this is understanding how a pressure works in terms of a piston. A lot of times in thermodynamics and gas law type problems, simply drawing a picture of a piston will solidify the concept of what's going on in a given problem or in a given situation. It's just it's a conceptual construction. Again, which statement best describes the final result when the gas is cooled? So as a gas is cooled, the pressure of a gas, does it increase? No, it decreases. The pressure decreases, the volume decreases. And so both pressure and volume change because P times V is equal to T times RT, right? So PV equals nRT. Always look at PV equals nRT and ask yourself, what does that mean in terms of all of these different kinds of changes? Now, that was sort of a whirlwind explanation of the kinetic theory. There's a lot more to it than that, especially if we start looking at interactions of gases. I'm going to fast forward a little bit to get to that, and and look at real gases rather than talking about diffusion and diffusion before we talk about diffusion and diffusion, just to tie things together with real gases and non-ideal gases. So the ideal gas is simply something that an ideal gas obeys the ideal gas equations. An ideal gas this is the equation of state. PV equals nRT. That's the ideal gas equation. So if a gas obeys that equation, it's called an ideal gas. So that defines an ideal gas. However, real gases, a real gas has a couple problems, has some changes. And the ideal gas says that the size of the atom is very small compared to the volume, and that they don't interact with each other at all. And so to correct for that, well, I mean, a real gas has atoms occupy space, i.e. volume, and atoms attract each other. I mean, they repel at short range as well, but this is this issue of excluded volume. So we can make a plot of, if I say let's look at n equals 1 mole, I can define a number called the compressibility factor, Z, which is PV divided by RT. Okay, this is called the compressibility. Okay, and an ideal is equal to 1. Ideal gas has a compressibility factor of 1. Now, if I look at the compressibility of a real gas versus various quantities of pressure, let's say P in atmosphere, let's say Z equals 1 for an ideal gas. At low pressure, all gases must look ideal, and so certain gases, H2 for example, has that behavior. CO2 has a behavior that looks sort of like this. Methane gas has behaviors that look like this. So in other words, at very, very low pressure, I see the effect of I see what's called deviation from ideal behavior. So this negative deviation at low pressure, this is due to the fact that atoms attract. Okay, initially that atoms are going to attract each other. This positive deviation from ideality is due to excluded volume. So as I increase the pressure, atoms start feeling each other more and more. So I get a higher compressibility factor than at low. So in fact, it's this kind of behavior that gives rise to the phase transition between liquids and gases, and an equation is called the van der Waals equation. So the van der Waals equation is the first attempt to make a correction, and I think it's one of the more useful equations of state to examine. And the van der Waals equation, the van der Waals, we can understand in the following way. So this is the pressure plus a van der Waals constant A times the density, number of moles per volume squared, this goes as the density squared, times the volume minus N times B, and that's equal to RT. Now A is an indication of the the attractiveness and B, rather N times B is the volume occupied by 1 mole of atoms, and it's not 22.7 22.4 liters. It's actually, you know, here's an atom. It's what is this little volume? You know, here's, you know, B is the atom, is the atomic volume. It's how much volume does one atom actually occupy, or does one molecule occupy? And A and B are called the van der Waals constants. And you have to look these up for a given, each atom or each molecular species that is described by the van der Waals equation has its own A and B parameters. They're called the van der Waals constants. Not so much constant, it's a van der Waals constant for a given species because they interact with each other in different ways. And that's right, this needs an end, and needs an end. Needs an end over here. Yeah, I usually write this in terms of a molar volume, and in which case this is the number of moles times B. So this is so B is actually the volume occupied by 1 mole of the atoms. Okay, it's the amount of space occupied by 1 mole of atoms scrunched all together as tightly as you possibly can, and it's these two modifications to the van der Waals equation of state give rise to phase transitions. So that's the only thing that we need to see a phase transition, i.e. going from liquid phase to a gas phase, is the inclusion of excluded volume and long-range attractions. And we're going to see that when we start talking about liquids. So the observed pressure is always, the observed pressure is lower than the expected pressure because of intermolecular attractions in real gases. They sort of pull each other together a little bit, and that increases as you get this little hydrogen, nitrogen, methane, and carbon dioxide, and this is the more polarizable, softer is one way to look at it. Of an atom has larger van der Waals constant. This is the van der Waals B, or the A constant. Of course, the bigger the molecule, the bigger the radius of the atom happens to be, B is bigger. So those are the two considerations that we have to take into account to look at real gases versus ideal gases. These are the A and B constants for various van der Waals constants for different species, and they vary all over the place. Again, it's the correction. And we can derive this directly from a mean field theory for the interactions between gas molecules. So we can derive what that quantity happens to be specifically, and likewise, B is simply the volume for the excluded volume. How many liters per mole does 1 mole of water occupy? Now that's of water molecules. That's not the actual material water. That is the volume, liters per mole, of 1 molecule of water. How much these molecules push each other out of the way. I can't get them any closer together than that. Okay. So let's go back and talk about effusion. And sort of effusion is simply the passage of gas through a small opening. If you poke a hole in a bike tire, you get the gas going out, and that the Graham's law of effusion is simply that the rate of effusion the rates of fusion of different gases is related to the square root of the molar masses of the gas. And diffusion is different. Diffusion is the term that describes the mixing of gases. How well do they go? So if the fusion rate is simply related to the square root of the mass ratio. So we can look at the fusion rate of hydrogen and uranium hexafluoride. This was used originally, and so maybe if you follow the news in terms of in the way that you separate uranium to purify it by isotope is to look at the fusion rate of uranium hexafluoride and then separate things by mass. And of course, uranium hexafluoride is moving a lot slower than hydrogen, so I can calculate the fusion rates of the two by looking at the square root of the mass ratio. And so basically, hydrogen moves about 13 times, it fuses 13 times faster than a massive uranium hexafluoride molecule. Again, this is simply looking at the square root of the mass ratio. Diffusion is again looking at how well is like the mixing of different of these two atoms, and again the diffusion constant is going to be related to the mass ratio as well. And so the way you can do this, and a very easy way to look at the diffusion is go into a very still room, don't move, and open up a bottle of perfume, and the scent of that perfume will diffuse via molecular collisions, and eventually you'll smell this. Now I emphasize a still room because convection and mixing due to air currents will change this. So you need to do this in something that doesn't have mixing. But basically, diffusion is simply a random walk. So it is how well do these random walks occur, and so we can calculate the diffusion constant if we wanted to by looking at random walk type behavior. Okay, so those are two different types of processes: diffusion versus effusion. The atmosphere, of course, is this is a little bit of fun to read. As I go up in altitude, generally the temperature decreases. Up to a certain point, up to the troposphere, it tends to decrease, primarily because of lower air density and cooling effects. You get a little bit some craziness here in between because of the ozone layer and different effects, but basically the temperature decreases linearly for the most part as you get higher and higher and higher and higher. Well, I guess this is a logarithmic scale. This is altitude in kilometers, 1, 2, 4, 6, 8. So it goes up sort of exponentially down as I get higher and higher in altitude. So if you go climbing, or if you go into the mountains, as you go higher and higher up the mountain, you'll notice very, very significantly that it gets a lot colder. So you get snow on top of the mountains and no snow at the bottom of the mountains. And so anyway, I just simply invite you to read the rest of this. It is as examples of atmospheric chemistry. It's a very, very active area of research. A lot of atmospheric chemistry is dominated not necessarily by simply the mixing of gases, but it's also the fact that there are ice crystals and reactions that occur on ice crystals and so on. And so simply read over this issue, and this is all in the book, Pollution from Electricity, and basically how scrubbers work is sort of an interesting thing to read about as well. This is all in the textbook. That's easy enough to read. So anyway, I'm going to end here, and again, subscribe for some extra credit. Pass it on to your friends, and good luck, stay safe, and I hope you did well on your exam, and with that, I will end. Where's nice?